My name is Aryan and welcome to my physics video on double pendulum. The double pendulum is a simple system with very complex behavior. It consists of one pendulum attached to the end of another pendulum, thus creating a two-link pendulum system, as you can see in this image where you have this pendulum 1 and this pendulum 2. Even though it is a simple model, the motion of a double pendulum quickly becomes chaotic and seemingly random, and predicting this motion accurately poses a major challenge. And today I'll show you how we can model the physics of a double pendulum more easily using Lagrangian mechanics rather than Newtonian mechanics. So let's get started. First, some background. A single pendulum, as we can see in the first image, can be described by Newton's second law, and where the force on the pendulum bob, which is this one, is just a component of gravity along the swing angle. This is the swing angle, and by applying Newton's laws, we can quickly come up with equations of motions for this system. But for a double pendulum, which is the second image, we have to repeat this same process of finding forces and applying Newton's laws for both the bobs, while accounting for the motions of each bob on the other through this connecting arm. And this quickly becomes very complicated. Instead, we use Lagrangian mechanics. The Lagrangian accounts for both kinetic energy and potential energy of the system, and kinetic energy and potential energy is represented in just one function given by T minus U. So for this system, the assumptions we need to make are these two bobs are point masses in the system, the rods connecting those bobs to the wall and to each other are massless, and of course gravity is present. And then just by looking at the diagram and the coordinate systems, we can say that the kinetic energy is given as this formula and potential energy is given as this formula, and we'll just have to switch x1 prime, y1 prime with polar coordinates, and similarly with x1 and y1 and x2 and y2 with polar coordinates. And from these equations we can easily derive the equations of motions without even explicitly calculating the forces on the bobs. And this is how we can do that. So for that we need to take partial derivatives of this theta 1 and theta 2 in order to come up with these two equations of motions, first one for theta 1 and second one for theta 2. And that is all you need to define the motion of double pendulum completely, and you can solve these second order partial equations by numerically or by using Mathematica and come up with these motions. So now I have coded up these equations into Mathematica and we can visualize their motion using a simple simulation. So let's have a look. As you can see here, this is a simple system of two pendulums, and even a small change in the starting point leads to vastly different and unpredictable motions over time, and this sensitivity is the hallmark of chaotic systems. In summary, Lagrangian mechanics provides an elegant and simplified way to model the physics of complex systems like double pendulum. The behavior is chaotic, but by using principles of energy conservation, we can easily derive the equations that determine this chaos. And thank you for watching this video. If you have any questions, please let me know in the comment sections, and thank you.